In this subsection, we'll look at the predictive PID, and the ideas behind this predictive PID are very similar to the ideas behind the Smith predictor, but the predictive PID is more general in the sense that you can use it to control slow between quotes processes, where the slowness can come from a dead time, right? I also use the name delay, and in that case we'll have here a Smith predictor. But the slowness can also come from an apparent dead time, right? And in this case we have, for instance, several first order systems in series, a lag system, or the slowness can come from an inverse response, right? We have a 0 at the numerator that is to the right of the imaginary axis, and in these three cases, right, you can use the predictive PID to control the system. For the Smith predictor, we had used the model without the dynamics to generate a fast prediction, and we had used that fast prediction to control the system. Well, we can do something similar for the predictive PID. We need, between quotes, a fast model of the slow process. So what you could do, for instance, if you have a slow process with several time constants, right, and a gain, well, the fast model could be the gain with the main time constant, right? And you can then use that fast model to obtain a fast prediction of PV. Well, once you have this fast prediction of PV, you simply use it to control the system. So the controller will react as if this fast model of the system is the actual system, and what you have done is taken the slowness outside the control loop. Well, again, this is a good idea, but there are two aspects that we haven't taken into account. Assume that this process has gain Kp and that here the gain is Kp hat, right? Well, this controller, if it has integral action, will make sure that PV fast goes to set point, but since the gains are different here, the actual PV will not go to set point. So we have a problem for set point tracking, but we also have a problem for disturbance rejection, right? Because the output disturbance that is acting on PV is not seen in this control mechanism, so we are not able to reject a disturbance. Well, this is not a problem. We know how to proceed. We use the same ID as with the Smith predictor, and what we'll do is use a slow model of the process. This model will have the same static gain as the fast model. Actually, the slow model will be the fast model where we add the dynamics that we had neglected in our model to obtain this fast model, right? So by comparing the output of the slow model, this slow PV, and by comparing it to the actual PV, we can detect if there is a disturbance, and we can detect if there is here a model error, for instance a mistake in the static gain. And by comparing the two, well, we obtain the model error that we now can use in our control. And we can use this error as follows. Again, here we have exactly the same ID. The predicted PV is the output of the fast PV plus the model error. Well, assuming that we have a stable closed loop, we can show that in steady state PV will be going to set point. So here again, we'll assume that we have integral action, right? So in steady state, we will have that, well, the predicted PV is equal to the set point, right? So if we look at this here in steady state, then we can replace the slow process by a gain Kp, right? This is the, well, steady state relation. Here we'll have a gain Kp hat and here a gain Kp hat, right? So as you can see here, you will have the influence, and here we can again assume that we have a disturbance that is constant, right? So here we'll have Kp, Mv and d, right? And here we'll have minus Kp hat Mv, right, coming from here, and here we'll have plus Kp hat Mv. So this one and this one will cancel out, right? And it's therefore very important, of course, that the gain in the slow model is equal to the gain in the fast model, otherwise they would not cancel out, right? But if the two gains are the same, well, we can see here that the predicted PV is the set point, but is also equal to PV, of course, in steady state. So if the closed loop system is stable, PV is going to, well, evolve to a value that is the set point and will have a zero steady state error. Well, we can now apply this predictive PID to a process with inverse response. So the slowness will come from the inverse response. The system is stable, so T2 and T3 are positive, and we'll assume here that T2 is substantially larger than T3. So T2 here is the main time constant, and since we have an inverse response, we know that T1 is negative, right? So the fast model will be simply, well, keeping the main time constant, right? And we throw out the slowness, and here we throw out, well, the zero that is to the right of the imaginary axis. So our fast model will simply be this first order model, right? This one will be used to control the system, right? But we have to make sure that we detect, well, disturbances at the output, and that we see that there are, well, essentially static gain mismatches. And this you can do by comparing the overall model with the actual PV, and this comparison yields an error that you add. Predictive PIDs will allow you to control processes with an inverse response, and you know that a simple PI controller will lead to problems because an inverse response is far worse than a delay, and you know that if you have a delay that is substantial with respect to the main time constant, you already have problems with a PI controller or a PID controller. Okay, so if you have an inverse response, this will be, well, far worse. And using this predictive PID, well, you can kind of take out of the control loop this inverse response, as you will see from a simulation. Note that if the model is an exact representation of the actual system, the model error will be zero, and the controller will not even see an inverse response, as the PI controller will only see a first order dynamics. Note also that for the tuning of the PI controller, we can do as if the process is a first order system, because the predictive PID controller has removed the slowness, in this case, well, the lead system with negative lead time constant, out of the control loop. Let us now look at an example in Simulink. This example is available on the web page of the course. In this case, the process is a simple lead lag system. So one lag time constant. So it's the example of the slides with T2 is equal to 0. And indeed, you can see that the lead time constant is negative. So the process has an inverse response. Let us have a look in the faceplate. As is usual for that type of controller, we have to give in the process parameters, right, the model parameters. And here for the tuning of the PI controller, well, we need to give in the closed loop desired time constant, and it's going to be set as gamma 0.25 here times the open loop lag time constant, right? So here we are going to use again IMC PID tuning, and we can do as if the process is a first order system, because the predictive PID will take this lead system with negative time constant out of the control loop. Well, let us have a look below the mask, and you see something very similar to what you have seen with the Smith predictor. So this is the output of the control that goes to the process, and we collect PV. So here in between you have the actual system, right? Here we have the model without the 0. So here we have the first order system, right, as you can see over here. And here we have the overall model, so that's the lead lag system, so the model with the 0, and this is indeed the case. For feedback, it's the model without the 0 that is used, and we have to add, well, the model error. So that's the difference between PV and the slow PV coming from the overall model with 0. And again, here we can see that indeed we have used this IMC tuning, and that we have used parameters corresponding to a first order system, and this here is the desired closed loop time constant. Well, let us now run this predictive PID with the exact model parameters, and this is what you obtain. So here we have here a set point change of 10, so at this time an error of 10, and since we want to accelerate the closed loop system so that the closed loop time constant is 4 times smaller than the open loop time constant and the gain of the process is 1, well, we have this, well, proportional kick here of 40, and as you can see, as far as the controller is concerned, everything looks as if the process is a first order type process, right? So you can see that the decrease here is looking like that of a first order system, and this is because the model is exact, of course. You can see, of course, that the actual system, right, in green, it's behind the red one, and because the PV and the slow PV in red are exactly the same, reacts with the inverse response. Also, the fast PV and the predicted PV are one on another, right? The blue one is below, and this is again because there is no model error. Note that since we have used IMC tuning, it's very easy to slow down the closed loop response, since we are working directly with the closed loop time constant as a function of the open loop time constant. For instance, if we put here 0.5, we can see that, well, the closed loop time constant has of course been increased, but also that the aggressiveness, and in this case the proportional kick, has been decreased by a factor 2. Well, let us look at the situation where the model is not exact, and what we'll do is change the gain and do as if we think that the gain is 0.8, whereas the actual process gain is 1, and we can then run the system. This is what you obtain. Since we have a lead lag system here and we have the wrong gain, well, the actual process and the fast process react immediately, and there is directly a difference, a model error of 10, right? And this model error of 10 is added to the output of the fast PV. So we have now a predicted PV that goes in the wrong direction of, well, 10. So we have a control error of 20, right? We want to accelerate the system with a closed loop time constant that is 4 times smaller than the open loop time constant, where the gain of the process is 0.8, and this will give an increase of 5. So the gain of the controller is 5 here, leading to this, well, proportional kick of 100, right? But again, you can see that PV is going to set point. This is guaranteed using this predictive PID controller as long as the, well, closed loop is stable, of course. And again, you can see clearly from the error that there is something wrong with the gain of the model. When you see a constant deviation in steady state, this means that you have to adapt the model gain. If the slowness in the process comes from a dead time, you can, well, draw the predictive PID like so. The slow model is the overall model of the process, so the model of the dynamics without dead time followed by the actual dead time, and the fast model is simply the model of the dynamics without the dead time, right? So this is then a predictive PID controller, but as you can see, we're using this model of the dynamics without dead time 2 times. So instead of doing this, what we could do is, well, take this signal over here from here, and this is what is done here, and this is of course a Smith predictor. Okay, so you can see that a Smith predictor is a special case of a predictive PID, but specialized for processes with delay. Well, the predictive PID controller can often be used as an alternative for a cascade. Remember that in a cascade you have to tune 2 PID controllers and you have to implement this interlock strategy, which could sometimes be heavy, so an alternative is sometimes used. Remember that one of the reasons to use a cascade is that if you have a load disturbance over here, with a cascade control, this will be immediately detected on PV1 and the inner loop will react. If you do not implement a cascade solution here and you only work with the control of PV2 using one controller and that you don't have this inner loop, well, if you have a load disturbance, it will only be detected when it's visible on PV2 and therefore it will be too late. So a cascade offers a more rapid rejection of load disturbances, and we'll have to look if this alternative for the cascade is also capable of a rapid rejection of the load disturbance. Well, the alternative for the cascade will be to implement a predictive PID. Remember that PV1 here is the PV1 that was used in the inner loop, and this is the PV2 used in the outer loop. The process is therefore decomposed in 2 parts: a fast process, that's the one that is in the inner loop, and the slow process, the one in the outer loop. And by definition, because we have used a cascade before, well, this process is much faster than this process. Well, in order to implement a predictive PID, what we'll do is use a fast model of this process 2, and we'll control the system with a PID controller as if the process is the fast process 1 followed by the fast model of process 2. Right? So what we have done with this predictive PID is take out the slowness of process 2 out of the control loop, right? So we'll be able to tune the PID controller as if the process is this one followed by this one. Very often this fast model of the process will simply be a static gain, the static gain in the relation from PV1 to PV2. Right? So the advantage with this predictive PID is that we only have, well, one controller. The question is now, if we have a load disturbance, will we be able to reject it as fast as with a cascade? And the answer is yes, because we're going to see it in PV1. And since this is a fast model of the process, we're going to see it very fast in PV2 as well, especially if this is simply a gain. So again, we'll be able to reject the load disturbance in a rapid way. As usual, what we'll do is use a slow model of process 2 in parallel, well, to detect disturbances on the output and to see if there are, well, errors in the static gain. So what we do is compare PV2 with PV2 slow, compute the model error, and this model error is added on top of the, well, fast PV2 to obtain a PV2 predicted. This is an example where cascade control can be replaced by a predictive PID controller to produce overheated or superheated steam in a power plant or for processes such as paper machines, where the steam is used in the drying section. Well, the steam coming out of the boiler is passed through an overheater or a superheater, right? And steam coolers are used to control the temperature by injecting or spraying water directly into the steam flow. The temperature is measured at the entrance and exit of the overheater, and since the water injection has a direct influence on T1 and that it takes more time to see the influence of T2, here it clearly makes sense to use a cascaded control structure for the temperature control. Well, sometimes, in order not to have to implement this cascaded solution, which requires two controllers that you have to tune with an interlock strategy, the following predictive PID controller is implemented. You recognize the fast model of the process in between T1 and T2, right? So that, well, the PID controller here is tuned to control the system from MV to the fast T2. So this is the dynamics of MV to T1, and then followed by the fast model, which very often is simply a gain. Here, of course, we need a slow model of the process to detect disturbances at the output and, well, to correct for a static gain that could be wrong, right? In this case, the dynamics from T1 to T2 is very slow. You can model it by a fourth order lag system with 4 identical time constants. In this subsection, we investigate scheduling. Gain scheduling, which means that the controller gain is adapted according to the working point, and controller scheduling, which means that all parameters, gain, integral and derivative time constants, are adapted according to this working point. We have seen previously that the system can be non-linear. This means that if you perform an open loop step response, here with a step of delta V that is 10, well, the response might be very different if you look at a change from 0 to 10, or a change from 40 to 50, or a change from 80 to 90. As you can see, in this first case, the gain is roughly 2.5 and the time constant is 15 seconds. In the second case, well, the gain is 0.9 and the time constant has been reduced to 5. And in this third case, well, the gain of the process around that operating point is further decreased, and this is also the case for the time constant. As you can see, the behavior is very different around these three operating points, so you can expect different controllers, different control action around the different operating points, and it will achieve this using gain scheduling, so adaptation of the controller gain, and controller scheduling, so this is adaptation of all tuning parameters according to the operating point. Well, let us have a look at our example of the preheating furnace, and we'll see also gain variation around different operating points. So let us assume here that in open loop that we perform a step change of delta MV over here, right? And we'll consider two product flows, FP1 and FP2, and we'll say that FP1 is smaller than FP2, right? So, well, if we do a step change over here, we'll have a variation of the temperature, and we'll have a delta of the output temperature in the first case, right? And we'll also have a delta of the temperature in the second case over here. But opening the valve here corresponds to a delta in the energy that we put in the system. But in the first case, since the product flow is, well, smaller, this is going to lead to a delta in the temperature that is higher than the delta in temperature in the second case. So we have that this delta over here is larger than this delta. So this means that we have here KP1, the gain around this operating point is larger than the gain around this operating point. So intuition tells us that the gain is high for low product flows and that it is decreasing with increasing product flow. So we'll have something that looks like this, right? So we'll have here product flow. Here we have KP, and we'll have a relation that looks like this, right? So if we now tune, for instance, a controller very aggressively around this working point over here, right? What will happen if the product flow is decreasing? Well, we'll have a situation where the loop gain, the static loop gain, will increase, and this could lead to instability. Since we have tuned the controller aggressively over here and we have imposed a certain gain margin, if we decrease the product flow, well, we could have a serious increase in the gain of the process, and this could lead to an increase in the static loop gain, thereby reducing seriously the gain margin up to a point where you could even go to instability. So we have to kind of adapt the controller gain to the product flow in such a way that we can maintain the loop gain, the static loop gain, constant over all the operating points. These are the two equations that we have seen when implementing the static feed forward. The first equation computes the required energy flow to bring a given product flow from the input temperature to the output set point temperature. The second equation gives you the delivered energy flow that is corresponding to a given fuel flow, and if you equate both equations, neglecting of course the losses, you could pre-compute the fuel flow. We can use those two equations to validate our intuition that the gain is varying with the operating point. So again, we'll equate the two equations, right? But instead of isolating the fuel flow, this time we will isolate the output temperature, and this is what you obtain. And what is interesting to us is the relation from, and this is the static relation, the relation from fuel flow to output temperature. And indeed we see here this dependence on the product flow in 1 over x, right? So you can rewrite it like this, and we see that the process gain is proportional to 1 over the product flow, right? So clearly the static gain is operating point dependent, and this is a situation that occurs very often in the process industry, and a lot of the problems associated with oscillations can be linked to variations in the static gain of the process. The solution is very simple. We can make the controller gain simply proportional to the product flow. So the solution is very simple. We tune the controller and we'll obtain, for instance, a controller gain KC0 for the operating point FP0, right? And then we can adapt the gain as follows. We'll take KC0, right, and we'll multiply by product flow over this product flow over here, right? You can see here that of course for this product flow FP0 we obtain the controller gain that we had during tuning, and we adapt proportionally to the product flow, and this is called gain scheduling, right? And the adaptation variable is the product flow, and this is called the scheduling variable, and in this case, as I said, it's the product flow FP. So in summary, we have seen that the gain from product flow to output temperature is operating point dependent, and if you tune the controller aggressively at a point where the product flow is high, this could lead to problems when the product flow is low, and this will influence the quality of the response of the output temperature controller. The solution is to implement gain scheduling to adapt the controller gain, right? Another solution, which is not very good, is of course to use a conservative approach and to decrease the gain of the PID controller in such a way that this is working around every operating point, but this will lead to sluggish control, slow control. So the best procedure in this case is to use gain scheduling, really, and this is adapting the controller gain of the PID controller according to the product flow. So this product flow in this case is the gain scheduling variable. In cases where the product flow is not available for measurement, and if you have then access to the valve position, you could use this value, because it is representative of the product flow, as a gain scheduling variable. In summary, gain scheduling is applied for systems where you have nonlinearities and you see that the process dynamics is different around different operating points. So the first thing that you have to do is find a scheduling variable that is representative of the operating point. In our example, it was the product flow. For instance, in a paper machine, it's going to be probably the machine speed. Then what you have to do is, find a relation between this scheduling variable and the controller gain. And once you have this relation, you can use it to adapt the controller gain. Well, for the adaptation of the controller gain, it's very important that you use linear interpolation, right? So you could not have a situation where the gain is constant in this interval and then constant again in this interval and constant again in this interval, right? So that you have this staircase evolution of the gain with the gain scheduling variable. This is forbidden because here you have a discontinuity in the gain. So when you adapt and you're in a situation where the control error is non-zero, this is going to lead to jumps in MV, right? And this is because the proportional action is leading to an immediate change when there is an error if you change the controller gain. Note that in the example of the preheating furnace, we had found this relation here between the gain scheduling variable and Kp from physics, right? In some cases, it's difficult, impossible to find this relation by looking at equations. So what you can do is work around several working points and obtain the gain experimentally, right? So that you kind of obtain the gain by, for instance, doing an open loop step response around different operating points, and you can then use the gain around the different operating points to come up with a relation that will now link the controller gain to the gain scheduling variable. We have seen that the objective of gain scheduling is to have control over a wide range of operations using more aggressive controllers. The alternative was to use one controller set of parameters, right? And to have sluggish control around many operating points. Well, what you're actually doing is make the closed loop system from set point to PV as linear as possible. The approach, as we have seen, is to adjust the controller gain based on a measurement that is an indicative value of the operating point. So it's based on a scheduling variable. We have seen the case with the product flow, right? And this is really a variable that is indicative of the throughput, right? And this is often the case with gain scheduling variables. Other examples are, for instance, the machine speed, the production rate, and so on. And of course, you'll need knowledge on how the process gain changes with these measured variables. And as I've shown, you can of course use experimentation to determine this relation, right? What is sometimes done is, instead of using gain scheduling, that we put the controller parameters in a recipe. And this is sometimes done in the paper industry, for instance. Each paper grade type of paper is produced with a certain speed, right? So if you put in the recipe different controller parameters according to the type of paper that you're producing, you're actually adapting the controller parameters to the operational point, right? To the actual speed associated to that type of paper grade. Well, the important choices for gain scheduling are obviously first the scheduling variable, right? And then, well, how many points you have in your adaptation of, for instance, the controller gain, right? So here you have your variable and here your gain, right? If you have to work experimentally, well, then obviously you do not want to take 10,000 points over here, and you're going to reduce the number of points considered, because each time you have to do an experiment to obtain the process gain first and then to obtain the controller gain, right? So these number of points here in the adaptation is important. And then you also have to look at the interpolation, right? We have seen that if you have, for instance, around these 3 operating points, this controller gain, well, you cannot use a staircase adaptation for the gain, and you'll have to do it as follows, right? In order to have a bumpless parameter change, and this is very important for the controller gain. Note that, for instance, if you would do the adaptation of the integral time constant, then this type of adaptation in staircase form is not forbidden, right? Because, well, the integral action imposes a gradual change. So even if there is a discontinuity in Ti, this will not cause jumps in MV, though this will only cause change of slopes in MV, right? So depending on the parameter that you're adapting, because now we have been discussing gain scheduling, but you can imagine that this ID can be also extended to the adaptation of other parameters. What is also very important is that you have a good human-machine interface where the operator can see what is actually happening during this gain scheduling procedure. So far we have considered continuous processes, 24 hours a day, 7 days a week, so that the plants operate for weeks without stopping. In contrast, in a batch process, the output appears in quantities of materials or batches. Batch processes are used widely in the pharmaceutical industry, and a batch process has typically a beginning and an end. For such a type of process, the gain scheduling variable is often time. Well, we have seen so far examples where the process gain, Kp, is evolving as a function of a gain scheduling variable, so that you look at different operating points and you can kind of see that, for instance, the gain is decreasing, right? That you have a relation that is like this. But you can imagine that something similar can happen for changes in the delay or changes in the main time constant. There is actually an example that I will leave for your information that shows that, well, with a change of the scheduling variable, you can see the main time constant evolve, right? So you could have here an evolution, for instance, of the main time constant that might, let us say, evolve like this, and then you have something similar for well, the delay in the system, right? That it goes like this, and these are just examples. What you can then do is take this evolution, and here we make the assumption that we have looked at approximations of the systems that are Broida models, right? Again, a time constant and a delay, and then use the IMC PID tuning method to obtain the corresponding variations in the controller gain in the integral time constant, and you could even take the derivative time constants, although this is not often done, and you find the corresponding, well, variation of the controller gain and the integral time constant as a function of the scheduling variable, right? And then you extend this idea of gain scheduling to simply controller scheduling. And again, sometimes what is done, instead of implementing it this way, well, this adaptation is implemented in the recipe, so that, well, depending on the product that is produced, of course the gain scheduling variable will change, but in the recipe you have values of the controller gain and the integral time constant. So according to the recipe, these controller parameters are simply adapted. Well, let us have a look at our example of the control of a preheating furnace implemented in Siemens PCS7, right, using an emulated process. We can have a look at the preheater control, and what you see over here is the master controller. But as you can see, the controller gain, the integral time constant, and the derivative time constant are coming from a block that is doing gain scheduling, right? So without a surprise, the scheduling variable here in this block X is the product flow, as you can see. In this block you can have, well, 3 operating points. So here 100 liters per minute, 500 liters per minute, and 900 liters per minute for the product flow. And here you have the associated controller gain, right? So in between there will be linear interpolation. As you can see here, TI is constant and TD is constant. So here really we are implementing gain scheduling and not controller scheduling. Well, we can now have a look at this master temperature controller in WinCC. Here it is, and if we have a look at the control parameters, here they are. Since we have used this gain scheduling block in CFC, at compilation, when mapping all the variables, a button gain scheduler is created. This button will appear automatically in the faceplate in the PID controller, and if you click on it, well, you have a nice interface that, well, tells you, well, you're at this operating point, 800 liters per minute, and the gain is, well, 0.64. As announced, the integral time constant and the derivative time constant are constant, right? So if you go and have a look, you can see here the 3 operating points, right, and the values of the gain. And since you're at 800, you can see here that indeed you're somewhere here in between, closer to 900, and this corresponds to a gain of 0.64. So what we can now do is do a change here in the product flow, and we should see here that this gain is evolving, right? So if we go, for instance, to 900, so we should have the value of 0.72 there. You can see clearly that the gain is evolving. Of course, at the same time, you see that the process is reacting, and since we have here a feed forward on the product flow, you can see that the temperature is not reacting to this product flow. This is something that we have seen before. Well, you might ask also, why is it necessary to have gain scheduling in here? Because the feed forward is doing most of the job. Well, this is true, but the temperature controller is assisting, so it is making sense to adapt the controller gain to the working point. I will leave the subsection on pH control for your information. You will see that the process becomes highly nonlinear, and one of the solutions is to implement gain scheduling. Well, in this last subsection of section 6, we look at loop interaction or coupling effects. We'll consider the most simple case, so a 2x2 multivariable process, right? And as you can see, for instance, the first output is influenced by the first input, but also by the second input. So here P11 is the relation from MV1 to PV1, and it is a dynamic relation, so this is here a transfer function, right? But PV1 is also influenced by MV2 through this other transfer function here, P12. So Pij here is the process that links the input MVJ to the output PVI. So in this 2x2 multivariable process, there are 4 transfer functions. Well, mathematically, you can write things as follows, and here you can see that PV1 is P11 MV1 plus P12 MV2, and this is precisely what we had seen in the previous block diagram. So this is here a transfer function, this is a transfer function, so on. So here we have a matrix, and this is called a transfer matrix. So you see here P in bold. This is meaning that there is a transfer matrix. There are 2 inputs, 2 outputs, so this must be a 2x2 transfer matrix. It's in bold, so it means that it is a matrix. So an example is this one over here, and here in this case, well, the 4 transfer functions are Broida models with different gains, different time constants, and different delays, right? Well, as you can see, well, this is going to lead to loop interaction or coupling, right? And this means that MV1 influences not only PV1, but it also influences PV2, and we have something similar for MV2. So if you look for single loop solutions, for instance, that you control PV1 using MV1 and PV2 using MV2, you could have the situation where the 2 controllers interact with one another. The next slide that I will leave for your information explores if it is necessary to take the coupling into account, and if so, how you should choose the correct pairing. This is called relative gain analysis, and it is especially useful when the complexity increases. Indeed, in the 2x2 case, the analysis is not that difficult. Indeed, if the gains in this transfer matrix are as follows. So for instance, here around 1, here around 1, and let us say here 0.05 and here 0.06, right? Well, then it's kind of obvious that you will control PV1 using MV1 and PV2 using MV2, and the coupling effects are well, negligible. If you have a situation that is like this one, 0.05 over here, 1 over here, 1 over here, and 0.06 over here, then of course you will change the pairing and you will control PV1 using MV2 and PV2 using MV1. Of course, if, well, the gains are similar, then you will have difficulties in using a single loop solution, except if you do decoupling, and this is what we are going to explore next. Well, let us have a look at dynamic decoupling. We can see here that PV1 is linked to MV1, and we can see this signal here, this influence from MV2, as a disturbance, right? So we can use IDs that are very similar to feed forward and implement a dynamic decoupling, that is this one over here. Well, as with this feed forward ID, the idea is to create a second influence path that will cancel the first one. So here MV2, right, is influencing PV1 through this path, and what we'll do is create another path of influence that goes through P11, right? We have a minus sign here, so we have to make sure that this first part is compensated by this second part over here. So we'll have D21 P11 is equal to P12. So obviously T21 is P12 over P11, as you see over here, and you can do something very similar for D12. As with feed forward, it is not always possible to implement a theoretical perfect decoupling, and if you remember the ideas from feed forward, you should remember that there could be delay problems. Imagine here that the delay in P11 is higher than the delay in P12, then the decoupling will not be perfect. There could be unstable pole zero cancellations in the perfect decoupling, and they are forbidden. And also this transfer function has to be proper, and ensuring properness is maybe going to make sure that your decoupling is no longer perfect anymore. Well, this idea of dynamic decoupling is illustrated here for the 2x2 case. It is possible to extend the ideas to multivariable systems that are more complex, but stick to the 2x2 situation because, well, extending this solution would be difficult to implement and to maintain. Well, let us have a look at this dynamic decoupling more in detail. We have that MV1 is equal to MV1 bar minus D21 MV2, and we have that MV2, it's MV2 bar of course here, is MV2 bar minus D12 MV1 bar. So PV1 is P11 MV1, so we can plug this expression in, right? And plus P12 MV2, and we can of course plug in the other expression, so MV2 bar minus D12 MV1 bar. What we can now do is rewrite this and organize things differently, right? So what we'll have over here is PV1 is P11, so we'll take all terms involving MV1 bar. So we'll have here minus P12 D12 MV1 bar, and we'll regroup the terms involving MV2 bar, and we'll have here, well, P12 minus P11 D21 MV2 bar, right? So by setting D21 to P12 over P11, we can take this one out and we have decoupled the system. But the reason I'm doing this calculation is to show you that you also have changed the transfer function from MV1, the new input MV1 bar, to PV1. And you can do obviously the same kind of exercise with PV2. Sometimes the coupling is mostly static and there is no coupling in the dynamics. So here we have separated what comes from the dynamics and what comes from, well, the gains. So what is static, right? And you can see here in this matrix that this one is diagonal. So this here is P11, and you can see that P12 is 0, P21 is 0, and this one here plays the role P22. So here in the dynamics there is no coupling, but there is only coupling in the gains over here. So the coupling is indeed static. And to show you graphically, this is how it looks like. You have only two processes, but the input of the two processes depends on MV1 and MV2 through this static coupling that you can, well, represent using matrices, right? So you have a static coupling matrix K, and it's general, right? And here you have decoupled dynamics, right? So you have the input MV1, this is what you can access, and internally in the system it is as if you have two coupled inputs and they go into decoupled dynamics to produce PV1. But the important thing is that the coupling is purely in the form of the static gain, and you have a static coupling matrix. Well, the following slide is for your information only. We are in the case here where we have only static coupling, and what you can then do is, of course, static decoupling. And the idea is as follows. We have a process with two inputs and two outputs, so the set point is also a vector with two outputs. And if you compare the set points with PV, what you have here is a control error, and we'll call this the coupled control error. What you can do is obtain the so-called decoupled control error, and it will be obtained from the coupled error by pre-multiplying by the inverse of the static coupling. So you need to experiment on the system to obtain this matrix, and then the decoupled error is simply the inverse of K times this vector, right? And now we have, well, E1D, right, E2D, and you can use, well, controls C1 and C2. Most cases there will be PID controllers, so you'll have PID1. This will produce MV1, right? And here, taking this second decoupled error, you'll have PID2, and it will produce MV2. Students in control engineering might remember that this type of static decoupling has been used for cross-directional grammage control for a paper machine. In that particular case, the coupling matrix is an n by n matrix, where n is the number of actuators, and this number of actuators can be as high as 100. If interested, this is explored further in the course Linear Algebra and Applications in the video about the paper machine application. So in this subsection we deal with statically coupled processes. So we have here MV1, MV2. There is a static coupling, right? So this produces here MV1C coupled, MV2C, and here you have P1, P2, right? And we have PV1, PV2. So this is a statically coupled process. And what we do is, well, use two PI controllers, PID. I'll write PI. So this is PI1, and here you have PI2. And we have, of course, a set point here, set point 1, and here a set point 2. Well, a second method, right, to do this static decoupling, and this is shown in the previous slides, right, but these slides are for your information, is to use two virtual signals, PV1 bar and PV2 bar, and to do the control on PV1 bar and PV2 bar. And as you can see, PV1 bar of course depends on PV1, but it also depends on the, well, set point and the PV of the other controller, right? And the interpretation is as follows. The signal PV1 bar is the prediction of PV1 if PV2 were on set point. Okay, so it is the value of PV that we would have with the same MV1, right, once this other controller would have brought PV2 on set point, right? So what we'll do is look at an example with static coupling and apply this methodology. Well, let us consider the following statically coupled process. We have a product here that goes through a heat exchanger, and at the exit of the heat exchanger the temperature is measured and the viscosity is measured. Both quantities have to be controlled. To influence temperature and viscosity we have two inputs. Well, the first one is used to add acetate, right? And this acetate will influence the viscosity. So by changing the position of this control valve, you can increase, decrease the amount of acetate that is added and influence the viscosity. Well, this acetate will have a certain temperature that in general will be different to the temperature that you desire at the output, but this influence will be rather small, and the influence of the acetate flow on the temperature will be small because, well, this acetate flow is small with respect to the product flow, right? To influence the temperature we can control the valve position to influence the cooling agent that goes through the heat exchanger, right? So this is one way to influence the temperature, right? But changing the temperature will also change the viscosity, right? So we can kind of see that the viscosity is influenced both by the valve position that controls the acetate flow and the valve position that controls the cooling agent flow. So we have here a strong coupling, whereas the temperature is mainly influenced by the flow of cooling agent. We have seen that, well, the flow of acetate has very little influence on the temperature, so that this coupling parameter here can be neglected. So what we can do over here is, well, control the temperature simply using this control valve. Okay, as we can see here, well, the temperature only depends on the position of this control valve, but we have a coupling effect in the sense that, well, both the acetate flow and the cooling agent flow will influence the viscosity. So what we'll do is use this virtual signal over here that will be acting as a prediction of the viscosity that you would have if the temperature controller is on set point. And instead of, well, controlling the actual viscosity, will control this virtual viscosity. Indeed, as I've said, the temperature is controlled using simply the cooling agent valve, and will control this virtual signal, right, using the acetate control valve. And this virtual signal is the actual signal, right, so the actual viscosity, and you have a term that looks at the control error in the other loop times a constant, right? And the interpretation of this signal is, well, that this is the value of the viscosity once the temperature controller will have done its job and brought the temperature on set point. It is a prediction that you should bring on the human machine interface, because this is an interesting signal for the operator and the process engineer. Well, with method 1 you really needed the static coupling matrix, right? This is this matrix with K11, K12, etc. Well, here you need this alpha, and in the slides that I have skipped, well, alpha is actually linked to these gains over here, but we will see that there is a methodology that allows you to find alpha without having to know the static coupling matrix. Let us have a look at the experimental determination of alpha. The first thing that you have to do, step 1, is to bring both the temperature and the viscosity on set point. Or what you could do is, for instance, work in manual mode and adjust the acetate and cooling agent flows until the temperature and the viscosity are on set point. It could be also that you have, well, controllers that are not very good in transient mode, right? Otherwise you would not optimize them, but that bring you to set point. So if this is the case, well, you can use those two controllers. In any way, you have to arrive in a situation where T and V are on a set point, and that you arrive at a steady state where both T and V are constant. Once V and T are on set point, we'll put the two controllers in manual mode, right? And we'll leave this position constant, and what we'll do here, and this is TCV, this is this control valve that adjusts the cooling agent. What we'll do, for instance, is we'll increase the position of this valve, and this will lead to more cooling agent, right? So the temperature that was on set point, okay, so this is the set point, and here everything was on the set point. Well, the temperature will decrease and it will settle out to some TPV, right? Of course, the viscosity was also on set point, but since the temperature is dropping, well, the viscosity of the product will increase, right? And in a steady state it will also settle out to some value VPV, right? So we have only changed the position of the valve controlling the cooling agent flow, and we have had that the temperature has decreased, right, and the viscosity has increased. Well, we can know here, because we have only changed this valve position, that this error here in the viscosity comes purely from the change in temperature. Okay, so what we can do is adjust alpha, right? And it's obvious that alpha will be negative here, because this one here, as you can see, is positive, and we have to decrease the viscosity, so alpha here will be smaller than 0. So we adjust alpha in such a way that the virtual viscosity, this one over here, is on set point again, right? So this virtual viscosity is the viscosity that you would have once this temperature is on set point again, right? So if now we would put both controllers in automatic again, well, this controller here would see a virtual viscosity on a set point and it would not react, and this is clearly what should happen, right? Because we know that the error in the viscosity comes from this control valve, right? And of course the temperature controller will start to react and adjust the cooling agent until the temperature is on set point again. But in the meantime, this controller will always see a viscosity that is on set point and will not react, and we have therefore decoupled the process. This concludes this section on recycling of the PID algorithm. As you can see, there are a few slides that I have skipped that deal with static coupling, with in addition different delays in the MV path. If interested, but this is only for your information, you will see that you can come back to the simpler solution of just static coupling by coordinating the MVs.